All right, so this is the last chapter that we cover in this class. Chapter 8 is about general linear transformations, or we're just going to call them linear transformations. Um, Linear transformations are kind of in a certain sense, you can think of them as one of the main topics of linear algebra. And we didn't really get to talk about them until the very end of the course. It's the way our book sort of structures things. But there's different approaches to teaching this course, and in some approaches, the concept of a linear transformation is introduced much earlier than we do. This is just the way our book approaches it, and so this is the way we structure the class, and that's totally fine. But let's get into the topic of linear transformation. So when we talk about a general linear transformation, we're talking about functions. A transformation is just a type of function. But we're being much more general with the types of functions that we're using in this section. If you've had, up through Calculus 1 or Calculus 2, you have dealt with functions of this type. Functions of the form R to R. And what that means is that your functions in those classes, algebra, calculus 1 and 2, things like that, the inputs are real numbers and the outputs are also real numbers. So that's what this notation means. This is giving me my domain, so the set of inputs, and this is actually not the range. We call this a codomain. It's not a term I'm going to be super strict that you're, using in this class, but we do make a distinction between this and the range. The range is a subset of this. We'll talk about range a little bit later. So domain and codomain. This is the set that contains all of the outputs and potentially other values as well. That is basically the extent of what you have dealt with as far as functions are concerned if you've had up through Calculus 2. Now, Calculus 3, you talk about a little bit more general types of functions that take inputs from Rn and provide outputs in Rm, where these can be different values. So if you've had Calculus 3, the terminology that's associated with this, just in case you want to know, if n is either 2 or 3, so a 2 space or 3 space, and this is R1, so this is just R, which means the inputs are vectors in 2 space or 3 space, and the outputs are scalars. In Calculus 3, we call that a scalar field. If n and m are greater than 1 but equal to each other. So if this is a function that goes from R2 into R2 or from R3 into R3, then what it's doing is it's taking inputs which are vectors, which you can also interpret as points in 2 or 3 space, and the outputs are vectors as well associated with those points. In Calculus 3, we refer to those types of functions as vector fields. So scalar fields and vector fields. That's Calculus 3 terminology. We're not going to use that terminology here really, but that's just to help you make a connection with something you may have seen before. Now, Rn, Rm, or just the special case of the real numbers R1, you can think of that as R1. These are vector spaces. We've been using these vector spaces a lot in this class. And these functions, we use the term map or mapping. They map values from this domain into this codomain. We want to be even more general than this. We would like to think about functions that map vectors from one vector space into some potentially completely different vector space. Or they could be the same vector space. But that's what we're dealing with here. So if v and w are just some general vector spaces, and t is a function that maps vectors in v into w, we say that it's a function that maps, or it's mapping v into w. Then that specific function t is a linear transformation if we have a couple of properties that we can verify. If for every scalar k and for every vector u and v in v, we have this property, this is homogeneity. So t of kv is equal to k t of v. So in other words, if I multiply, if I think of v as an input, right? into this function. If I multiply the input by a scalar, the result is the same as if I had just plugged v into my function, gotten an output, and then multiplied that output by the same scalar. Okay, so you can think of that k as being brought out of that transformation as well. We call this homogeneity. We've seen that name for similar properties with matrices and other things in the past. This is an additive property here. This is that t of u plus v is equal to t of u plus t of v. What this means is that your function t, if I were to take two vectors in the domain v and add them, and then plug that into my function, the result is the same as if I had plugged each of these vectors independently into that function t and then added the results. That's what this additivity property means. Functions that satisfy both of these properties are called linear transformations. In the overwhelming majority of functions that you can talk about that take a vector space v into a vector space w are not linear transformations. We're going to look at a bunch of examples of linear transformations and a couple of non-examples, which may lead you to believe that most functions are linear. That's not true at all. These are very strict conditions that a function needs to have in order to qualify to be a linear transformation. And a great deal of functions do not satisfy these both. Continuing with some of the terminology, if w is equal to v, which would mean that that's a case like this, where the domain and the codomain are the same vector space, then we are more specific that linear transformation t is specifically called a linear operator. So the term operator means that my inputs and my outputs come from the same set or the same vector space. Okay, so we're going to run through several examples, verify for most of these that we are looking at a linear transformation. So first of all, there's an entire section of your book devoted to these types of transformations, section 1.8, all the way back in chapter 1. These are called matrix transformations. If A is an m by n matrix, then the function, which we're always going to notate t with a subscript of a, that takes vectors from Rn into Rm, defined this way. So if I take a vector x, notice the domain is Rn, and I multiply x on the left by the matrix A. So that means I'm thinking of x as a column vector from Rn. Notice this multiplication would be defined because A is an m by n matrix, and representing x as a column matrix, it would be an n by 1 matrix, so that multiplication would be defined. Also, notice the output would be an m by 1 matrix, putting it in Rm. So this thing would live in Rm. This is a linear transformation, and it's a very, very important type that we call a matrix transformation. I'm going to talk about that in just a minute. First of all, make sure you understand that this thing does in fact act as a function that takes vectors from Rn into vectors in Rm. Now, to show that it's a linear transformation, what we do is we verify that our function satisfies both of these properties. So what we do is we say let x and y be vectors in Rn and k be any scalar. If you're asked to prove that a function is a linear transformation, you're always going to start with a statement like this, because we need vectors and a scalar to verify these properties. Okay, then ta of x plus y. I'm verifying the additivity property first, but it doesn't matter which one I do first. By definition, what we do when we plug vectors into this function is we multiply this vector, x plus y as a vector, single vector, on the left by a. That would look like this. So that's the definition of what this function does to that vector. Now, because this is matrix multiplication now, and we know that matrix multiplication has the distributive property, this is equal to ax plus ay, right? However, ax is the same thing as ta of x. Remember, that's what this function does. It multiplies x on the left by the matrix A. So this thing can be represented this way, and similarly, ay is equal to ta of y. Notice that verifies that additive property that we need linear transformations to satisfy. The homogeneity property is very similar. And TA of kx. Well, I can't just pull the k out immediately because I'm trying to verify that I'm allowed to do that. So instead I have to use the definition of the function to see what this thing looks like. A times kx. Okay. Well, we verified way back in chapter 1 that matrix multiplication has that homogeneity property as well, which means if you multiply a matrix times a scalar multiple of a matrix, that scalar multiple can be brought out here, and I can start by multiplying the two matrices together and then multiply by the scalar. We proved that property a long time ago. This, however, is the same thing as k times TA of x. Therefore, TA is linear. That I can say that, and that means the same thing as TA is a linear transformation, which is sometimes we just say is linear. Okay, so this thing is a linear transformation. Now, I put this example first because, again, section 8.1, we talk about matrix transformations in depth. But as we're going to see as we progress through chapter 8, every linear transformation, every single linear transformation, regardless of what these vector spaces are, as long as they're finite dimensional, that's kind of the one condition that needs to be in place there. Every linear transformation can be represented by a matrix transformation. So I'm not going to explain what that means quite yet because we have to work up to that point. But basically, if that's the case, then this matrix A characterizes all linear transformations. And for that reason, it's very much worth studying different properties that matrices can have. What if A is a symmetric matrix? What if A is an orthogonal matrix? What if it's a diagonal matrix? What does that say about the linear transformation that this thing represents? And you, thinking about this, you start to realize that all of the work that we've been doing to study matrices and all these different types of matrices is actually for the purpose of understanding these linear transformations more. So this is where things kind of start to come together a little bit. But again, we have to sort of work up to the point where we can see the connection between matrix transformations and all other linear transformations. We aren't there yet. What we should do is continue looking at different types of linear transformations. So here, let's let V and W be any vector spaces at all. We can define a transformation, a function that takes V into W, defined this way. T of V is equal to the 0 vector. Now notice, I'm just writing zero here, but you have to be thinking about what 0 that is. Because these are potentially two different vector spaces, which means the 0 vector in this vector space might be completely different than the 0 vector in this vector space. So when I write 0 here, notice it's the result of plugging V into this function, which means this is an output for this function. That would mean that this is the 0 vector of W, not the 0 vector of V. So what this is saying is that this is a function that maps any vector in V straight to the 0 vector of W. We call this the 0 transformation, and it is a linear transformation. To verify, again, we make a statement similar to what we started with. Let U and V be vectors in V, and K be a scalar. Okay. Then I want to verify that additivity and homogeneity property. So we're calling this T. I'm going to say then T of U plus V. Remember, the goal here is to show that this is the same as T of U plus T of V. But all I can work with is the definition of this function in order to make that happen. Well, it really doesn't matter what U and V are. U plus V is just going to be another vector in V, and T takes every vector in V and maps it to the 0 vector in W. Okay? But I know that the 0 vector is equal to the 0 vector plus the 0 vector. 0 plus 0 equals 0 for the zero vector of any vector space. We know this to be true. And this 0 can be thought of as t of u. This 0 can be thought of as t of v, since both of these, by definition, would have to equal 0 anyways. So we see that this additivity property holds. Homogeneity is very similar. Remember, I can't just pull the k out right away because I don't know that I can use that property yet. I have to show that that's a valid thing to do. So again, k times u would just be some vector in V, which means it gets mapped to the 0 vector. But I know that any scalar times the 0 vector is equal to the 0 vector. So this allows me to write k times t of u, because again, this 0 is what t of u would be equal to. That establishes homogeneity for me. Therefore, t is linear. Okay? That's an important linear transformation. I think sometimes we call that one the trivial linear transformation. Here's another one. Notice this one I use the symbol I instead of the more generic symbol t. Anytime we see an I, we're going to be thinking of this this particular linear transformation. So in this case, I am mapping a vector space into itself, which makes this transformation an operator. Remember, that's what the term operator means. If I define this linear or this operator to take vectors in V and map them to themselves, so I of V is equal to V for anything I plug in. The input and the output are the same. We call that the identity operator. And that shouldn't be surprising. You've talked about identity functions in algebra. It's the same idea. This is a linear transformation. So again, let u and v be elements of V, and k be a scalar. Then, okay, I of u plus v by definition is u plus v, because what this is doing is it's taking this vector and mapping it to itself. That's the definition of this thing. However, u is equal to I of u because I of u should take v to itself. And v is equal to I of v, and that establishes the additivity property right away. Homogeneity is just as simple. If I say, what is I of k times u? Well, the identity operator maps this vector to itself, but u, if I single out the u, is I of u, and that's being multiplied by that scalar k. So that gives me the homogeneity property very, very easily. Therefore, I is linear. Okay. Let's look at some more examples. It's worth getting a lot of examples under our belts here. This one, I'm actually going to skip the proof of this one. It's easy to do. Your book actually goes through this example as well. So if you want to see the verification, you can take a look in your book. But this one says that the function defined by t of p of x is equal to x times p of x. Then t is a linear transformation. First of all, notice it's taking polynomials in Pn and mapping them into polynomials of Pn plus 1. And it makes sense that the linear transformation would have to be of this form, because if p of x is an nth degree polynomial, remember this is the set of all, the vector space of all polynomials of degree n or less. But if it is an nth degree polynomial, then multiplying an nth degree polynomial by x will raise that degree by 1. So this is going to this mapping will have outputs that are that belong to p of n, sub n plus 1 here. T is a linear transformation, which you can verify. We're going to use this linear transformation in an example at the end of this section where we're done covering this. I will prove this one. This one's straightforward as well, but this is another transformation, linear transformation, that your book talks about in an example, and it's a very important one, which is why I want to include it here. This one, we call this one capital D because it stands for derivative. So remember C1 of negative infinity to infinity. What this means is it's the vector space of all continuously differentiable functions defined everywhere on the real line. And it's going to be mapped into the set of all functions that are defined everywhere, whether or not they're differentiable. The linear transformation. So this is a really important thing to kind of wrap your mind around. This linear transformation D is a function, but its inputs are also functions. So it's a function that has other functions as inputs. Okay, these are really important in a number of areas of math, these types of things. So the function takes D, or the linear transformation D, takes functions that are continuously differentiable, f of x, and maps them to their derivative. Okay, D then will be a linear transformation in this case. So to show this, let f and g be vectors in C1 from negative infinity to infinity. So that means these are continuously differentiable functions. And k is going to be any scalar. Okay, then remember what we want to show is additivity and homogeneity. So D of f of x plus g of x. These are the two functions that I want to add up. By definition, this is the derivative of these two functions. So I'm going to write that this way. Or sorry, it's the derivative of the sum, f of x plus g of x, like this. Okay. Now from calculus, we know that the derivative of a sum of differentiable functions is the sum of their derivatives, which means I could write this as f prime of x plus g prime of x. That's a property that we prove in calculus. But this is the same thing as d of f of x plus d of g of x. And that gives us our additivity property. Homogeneity is very similar. If I do d of k times f of x, remember that's the same thing as the derivative of the function k f of x, but we know from those properties of derivatives that you prove early on in a Calculus 1 class that this is the same thing as k times f prime, which would be k times d of f of x. So we have that homogeneity property as well. Therefore, d is linear. Okay? So several examples. We're going to talk about a theorem about linear transformations and then start looking at some non-examples just to show you what types of functions you can define between two vector spaces that don't satisfy those properties of linearity. But we're going to save that for the next video.